ready to go.
Perfect. Well, thank you very much, and thanks, Martin, for inviting me to Perth. And it's a great pleasure to be here. And as I said, I really enjoyed swimming in the Indian Ocean once I figured out it was the Indian Ocean, indeed. And thanks, guys, for coming, and to those of you who are online as well. So I'm going to be talking about photon counting CT today, and maybe why use it and maybe why not use it. And maybe somewhat going to try to persuade you to actually get a photon counting CT scanner, and you'll see why. And as Martin said, I'm from the University of Victoria in British Columbia, but I did not come here yesterday from BC. I came from Sydney, and I'm on my sabbatical in Sydney for 5 months now. So I'm only slightly jet lagged, not too much. All right, so let's. We are not using regular detectors. Sorry, you should have been here, guys. We are using photon counting detectors. So we'll be focusing on the detector side here. And in case you missed everything, this is just a brief introduction to CT imaging. The important stuff will be happening right now. And you should watch the video of the Neotom Alpha Siemens CT scanner, photon counting CT, because it's very interesting. All right. So, how do conventional detectors work? So again, we're talking about the detectors that you will have in a CT scanner in your small animal system, that you have it in the clinic, and most scanners work on this way. So we have an X-ray beam that interacts with a scintillator material typically, and these X-rays convert the energy into scintillation photons, so visible photons. They're then collecting on photodiodes, we get an electronic signal, integrate it, and we basically get the total energy absorbed in the scintillator, and this is our signal, and that relates then to what we are trying to process and reconstruct into a CT image. So if we have a spectrum of X-rays, unfortunately, that's what we have from X-ray tubes. It would be nice if we could have a monoenergetic beam, but that's not the case. And if we look at, let's say, the mean energy of these beams, around, let's say, 58 keV in this case, we only get so much contrast that corresponds to the difference in linear attenuation coefficient or mass attenuation coefficient as shown over here between the two materials. So for example, between soft tissue and bone, we would get, look, this is logarithmic scale, but we would get a certain contrast. So you can see that for high energies, you would get much lower contrast between these two tissues. For low energies, we would get higher contrast. But we only get basically one number out of this conventional CT image, and that's what you're used to. You scan a patient, a small animal, and you get one CT data set. And so this is an example of a phantom that we scanned in our photon-counting CT system. I'll talk about our system a little later. But you can see that it has 3 different contrast agents. Let's see, iodine in purple, gadolinium in green, and gold in yellow with different concentrations. And you see on this regular energy integrating VID CT image, it's difficult to basically distinguish the different concentrations. This is a combination of the two, of the all three contrast agents. So it's difficult to tell what is what material, because they just happen to have the same difference in linear attenuation coefficient, and we just cannot distinguish these two materials because they end up having the same CT number in the image. Now, if we go into photon counting CT, we are using photon counting detectors, and they are called sort of direct conversion detectors. So X-rays interact with a semiconductor material, they generate electron hole pairs, and the electrons are being attracted to the anodes because there's a high voltage potential applied between the two, and you collect the signal on these different channels. Then you process the signal, and you can distinguish the signal, and you can sort it basically in n different counters. This number n is the number of energy levels that you can have in your detector. And they can change from 2, which is basically dual energy CT, to typically 6, maybe I have seen 8 in some of the scanners. But of course, if you're processing the data into more channels, it's just gonna take longer. And that's basically been the main drawback of photon counting detectors, is that they cannot accept such high count rates that we are using in clinical CT scanning. So that's something that manufacturers of photon counting detectors had to work on. Anyway, so you get your signal, and you can set thresholds, and based on the threshold, the higher the signal, the higher the energy that is absorbed in the detector, and you can select these different energy bins. And of course, this is convenient, especially when you have a polyenergetic spectrum, because then you know what X-ray of what energy came into your detector, and you can relate it back to the incident spectrum. It's not extremely straightforward, but having the energy information helps you with CT images. Should help you at least. I'm just going to demonstrate on the phantom that we just talked about. Remember, there's different materials in the phantom: iodine, gadolinium, and gold. And here I'm going to be showing different images of different energy bins. So 23 to 33, 33 to 50, 50 to 64, 64 to 81, and 81 to 120 keV. If you know anything about X-ray fluorescence or kHs of materials, you know that these edges, 33, 50, and 81, are actually the kHs of the 3 different materials. I'll talk about kH imaging a little bit, but you can see that, for example, I think if you look at the gold material, which is shown over here, in principle, you should see lower contrast for high energy images, unless you're looking around the kH of the material. So the kH of gold is 81 keV, and so for this particle, 81 to 120 keV, the kH, the higher energy image now has higher contrast than the lower energy image. But that should be the opposite for all the other materials. So if we look at, for example, iodine here, so you see that the contrast in the lower energy image is higher than the contrast in the higher energy image. And I'll talk about this a little more and tell you about kH imaging, but basically this is the information that photon counting CT offers us, and hopefully we can take advantage of it. And I'll talk about how we can take advantage of it. All right, so basically, we do have our small experimental photon counting CT scanner at the University of Victoria, but fortunately, we are not the only ones who actually are working in the photon counting CT space. And there's Siemens provided, I believe, 3 photon counting CT prototypes. I think the one that Mayo Clinic that's shown over here was installed in 2015. And it was actually used for patient images. So you can see their prototype scanner that was again installed in 2015 at Mayo Clinic with Dr. Fletcher and Dr. McCullough. So Dr. Fletcher is a physician, Dr. McCullough is a physicist, and they have been doing lots of photon counting CT imaging of patients as well. So most of the data they'll be showing today comes from their lab. There's also the Philips SPC-CT in Lyon. So that's another scanner that a prototype of a photon counting CT scanner. But of course, it's in France, and I like this logo, imaging all the photons, and just making sure that we get all the photons. And I hear that you guys might be interested in purchasing this Mars preclinical scanner. So it's somewhat different because it has a smaller bore. It comes from New Zealand, from Christchurch, from Mars Biomedical, I think that's how the company is called, but they are using it in some clinical trials to image wrist. So the bore is much smaller. You cannot put a patient or the body of a patient, but you can put a wrist into the scanner, and that's another photon counting CT scanner. Again, those have been available probably for the last 5 to 10 years, and people have been doing research with it, but it wasn't until last year when the first photon counting CT scanner was approved for clinical use in the US and in Europe as well. Okay, so I'm going to be talking about a few applications. Again, this will be work that has been done by other groups, not by my group, but eventually I'll talk about our system as well. So there's basically, when you talk to people about photon counting CT, there's basically two obvious advantages. One of them is the fact that since you get to select thresholds, you can basically select a threshold above the noise of the system. So that means that you should be able to get images that are less noisy, and that seems to be advantageous. The other advantage is high resolution. I'll talk about that later. So in this case, there's an image of a thorax phantom, and you see there's lots of streaking and lots of noise in the EID CT, and again, this is the energy integrating detector CT, which is the conventional CT that you would find in the clinic here, I'm sure, a number of them, and this is an image from photon counting CT. So you see that image noise is reduced. Visually, I'm sure if you did some analysis, you'll see lower image noise as well. So this is one of the examples of noise reduction. In this case, there's a patient image, and they see some basically more noise in the EID CT image as well. Those are paraspinal muscles, and here in the rib as well, you see that there is some more noise again in the EID CT image compared to the PCT-CT. It's also different because there's more beam hardening in EID CT. So all these artifacts combined make the PCT-CT image better, of higher quality. And in this case, this is actually a quantitative analysis. And if you focus maybe on the first two images, this is EID CT and PCT CT image of the same patients. And they did quantify the signal in the aorta. And you see that for the same imaging dose, the same beam parameters, they were getting noise of about 70 Hounsfield units in the EID CT, about half of that, 37 Hounsfield units in the PCT CT. And maybe even if you look at it, you could probably tell that this actual image, the PCT-CT image, is less noisy than the EID CT image. Maybe it's not super convincing from point of view of diagnosis, but it tells you quantitatively that PCT-CT produces lower noise. And if you are looking, for example, for an image that has a thinner slice thickness, then you can see that the noise of the 1 millimeter slice thickness acquired on the PCT-CT is the same as the noise for 2 millimeter slice thickness on the EID CT. In other words, noise reduction also means lower dose. So if you wanted to create same quality images, same noise with PCT-CT, then EID CT, we can just reduce the dose by a factor of 2 or so. So that's kind of interesting. Does it matter? Maybe we'll talk about that a little later. So noise reduction is one of the aspects, and the other one, the main important one, at least as far as I'm concerned, and I think as far as the community is concerned, is the increased spatial resolution. So these are images of a patient with endovascular stent graft, and again, this is the same imaging dose with 2 millimeter slice thickness and 1 millimeter slice thickness, and you can already tell that the spatial resolution, like the stent struts, can be much clearly visualized in the PCT-CT compared to the EID CT. It might be basically just due to the smaller slice thickness, because the stents, have really fine structure. And if you are now imaging 2 millimeters, you won't be able to see the stent struts as clearly in the EID-CT compared to the PCT-CT. And here on the right-hand side, they use basically the same 1 millimeter slice thickness with slightly different filter for the image reconstruction. And you can also see that it resulted in a much nicer, much sharper image. Here's some images of the inner ear, EID-CT on the left, PCT-CT on the right, and you can clearly see that there's the PCT-CT offers much higher resolution than the EID-CT. And the last one is the right images of the right temporal bone as well, and you can see that the stapes can be now visualized much better with much higher contrast because of the higher spatial resolution in the PCT-CT image compared to the EID-CT image. I know that this PCT-CT image has a slice thickness of 0.2 millimeters and EID-CT 0.4 millimeters, which is actually quite interesting because that's difficult to get on EID-CTs. And one of the reasons why we can actually get higher spatial resolution is that the pixel pitch or pixel sizes in PCT-CT can be smaller than EID-CT, and the signal doesn't spread as much inside the detector. So increased spatial resolution and decreased imaging noise, two main benefits of PCT-CT, at least as far as I'm concerned. Okay, so the next one is beam hardening reduction. So basically beam hardening occurs for low energy X-rays more so than for high energy X-rays. And this is actually shown on this data set, which is actually, I find it very interesting, and I haven't really read up too much on the history of PCT-CT, but you can see over here, this was apparently the first patient scanned with photon-counting CT. It's interesting, it was done in Israel by, I believe this was a GE scanner, which doesn't say over here, in 2008. But basically the GE scanner doesn't, there's not much more patient data from this scanner, and basically Siemens kind of took over with all their publications, at least on PCT-CT. But their first patient was scanned, as far as I know, well before the first Siemens scanner. Regardless, let's go into the images. So you see, this is the sagittal views, that the low energy X-rays create lots of beam hardening. They're typically visualized between bony structures. If you go to high energy, there is not that much beam hardening. And if you look at all the energy, there is, of course, some. So when you can select the high energy data, you can decrease beam hardening. But of course, the data is then more noisier because you're not using all the photons for image reconstruction. And that's shown again in here in the image of the brain. Another patient, on the left-hand side, we see the total image. Again, this would be sort of equivalent to energy integrating detectors. And then you can look at low energy data versus high energy data or high energy image. And basically the idea here is that for low energy data, you get better contrast between the gray and white matter. Of course, nowhere close to MR imaging, but for CT, this is pretty decent. However, you get some beam hardening artifacts is shown over here by these arrows. And again, both of these images are noisier than the image that was acquired with all photons because you're just using a subset of the data for image reconstruction. And here's another example of how photon-counting CT could help and potentially prevent misdiagnosis. So on the left-hand side, there's images of the same patients of their carotid artery. And you can see some petrous segments over here that create beam hardening artifacts in EID-CT. So if you look at the Hounsfield units, in between these two petrous segments, you actually see that the Hounsfield units decreased. And in principle, this could create or result in misdiagnosis. If you look at PCT-CT and you look at the difference, in Hounsfield units, you basically get rid of the beam hardening artifact here. So beam hardening reduction is offered by PCT-CT as well. Okay, and almost the last one is metal artifact reduction. And again, metal artifacts are more pronounced for low energy X-rays. So if we can pick the high energy X-rays in our image, we should be getting reduced metal artifacts. And this is the case for this patient who had fused lumbar spine. And you can see in the EID-CT, we see lots of metal artifacts. So basically, whenever you have two metals, the area between them shows up as air. And of course, we know that's not the case. But this is the cause of the fact that basically people, have different ideas about what is causing these metal artifacts, but basically we are not supposed to be seeing any signal in between these two screws when the X-rays go through the screws, but we see scatter. So now we have to make sure that, even though we see signal, we are just basically compensating by thinking, or the reconstruction algorithm is compensating by thinking that there is now no tissue, that there's only air because we see some signal. So there should be air as opposed to tissue, regardless. So this is EID-CT images of a patient with a lumbar spine. If you look at PCT-CT, of course, there's still some metal artifacts, but they are much reduced. So if you're looking, for example, at the vertebrae, you see it much nicer in PCT-CT compared to EID-CT. Now, there's a patient with unilateral hip prosthesis, and again, you see some air in this area that appears to be air, but it's not. And if you look at the PCT-CT image in panel B on the right-hand side, you see that these metal artifacts are much reduced in PCT-CT, again, because you can pick high-energy X-rays that don't suffer from metal artifacts. And here's the last patient data with, for a patient for a posterior rod and L5 to L2 to L5 screw fixation. So you see a lot of hardware in the patient. And if you image the patient with EID-CT, it's really difficult to see sort of what's in the middle, in between the metals. But if you image with PCT-CT with high-energy X-rays, you actually can see some, tissues in between the metals. On the right-hand side, this is just the same images, except with a different kernel and different window and level. And you can, again, see the improvement in image quality for PCT-CT. Now, the very last application from data from different groups would be on KH imaging. And I sort of alluded to that at the beginning of my talk. And the idea here is that if you're trying to image a high atomic number material, such as gold or iodine or gadolinium, as I've shown before, but I'll talk to you about different materials as well. If you look at their attenuation properties, they look something like that. They exhibit a KH at a certain energy that's specific to that particular atom. So for gold, for example, it's, I believe, 8179, around 81, I think, 81 keV. And we can take advantage of the fact that, again, the attenuation above the threshold is higher for gold than below the threshold, again, for 81 keV. But if we look at soft tissue, for example, there is very little difference in attenuation. So what we could do, we can set the threshold at the KH of the material, then one below, one above, and basically acquire X-rays above the KH. This is what we would get for a phantom. This is what we get for below KH, and we can just subtract these two images really simply by subtraction. And what we end up with would be just the image of the contrast agent. And you can do this if you have multiple thresholds. You can actually do this for multiple contrast agents in the same scan. So you'll end up with gold only. This is done for iodine imaging. So these are some images of a swine that was injected with iodine. So you can see basically the entire CT image, perfusion image on the left-hand side, and just the iodine map on the right-hand side. Again, this is done by KH imaging. And here there's some pictures of the canine infarcted myocardium. So they injected iodine and gadolinium contrast agents. The iodine basically just shows the blood pool, which is shown over here. So this is done by KH imaging of iodine, which is at, the KH is at 33 keV. Again, by simple subtraction. They looked at gadolinium as well. I believe the KH is about 54 keV. And you can see that for the gadolinium images, you actually can see the scar tissue, which you're not able to see with the iodine. Then you can look at the non-contrast map as well, which is not as interesting. But what is interesting here on the right-hand side, in the bottom on the right-hand side, is that you can see the blood pool sort of in green, but also the gadolinium scar tissue at the bottom. And if you contrast it with the regular EID image, then you basically see no difference in scar tissue in the gadolinium versus iodine contrast. So that's one of the ways how you can use basically what we call multiplexed imaging with photon-counting CT. So you can image multiple contrast agents at the same time. Seems like it has some application here in the infarcted myocardium imaging, but overall, how this can be used in the clinic is probably, somewhat questioned or questionable as well. Anyway, so what I'm going to do now, I'm going to talk about some of the research that we have done in our lab. So we have our lab is XSITE, so it stands for X-ray Cancer Imaging and Therapy Experimental Lab. And this is really the entirety of the lab space that I have. Maybe it's a little bigger, but not much bigger. And what we have here is basically just a system in which we rotate the sample. We don't rotate the gantry that has the X-ray tube and the detector. It's just much more complex. So we just, went the easy way, and we have a rotation stage in between the detector and the X-ray tube, and we just rotate the phantom or the object to be scanned. We have a regular X-ray tube that runs up to 160 kVp, but we usually use it at 120 kVp or kV for imaging, like people do in the clinic. And now we have a detector that has an active area of 0.8 times 190 millimeters square. Actually, I don't think that's correct. It should say 8 times 190 millimeters square. So it's about 20 centimeters in length and about 1 centimeter in height. So we are limited as to how large of an object we can scan, but it is much better than our first detector that was about 1 centimeter in length. So we had to do lots of crazy things to be able to actually scan with CT. We had to, at this point, we image a 10 centimeter diameter phantom that's shown over here, but we can image other objects as long as they fit in the field of view, which, if we push it, could be maybe 15 centimeters. But we had to perform geometrical calibration, which wasn't that easy. Energy calibration, I'll talk about that as well. And we're using RTK image reconstruction software. And again, the detector comes from Redland Technologies, who have been very helpful in our projects. And I would have to say that PCT-CT images did not come easy at all. So the very first images in 2019 looked like this. It was only a 2.5 centimeter diameter phantom. So we had to basically set the X-ray source, detector, and phantom, and then scan 360 degrees. Then we had to move the phantom slightly, so rotate again, move it again, and rotate again. So if you're familiar with CT history, it would be sort of called the second generation CT. So very painful for data acquisition and image reconstruction as well. That kind of shows here, the images were not very sharp, lots of artifacts, but we got CT images, which was quite exciting. I have talked to people from companies that were using the Redline detectors, and they were impressed that we were able to actually get CT images because in their companies were not. So we're quite happy with that. Well, fast forward to 2021, we actually got a larger detector, so we could now image a larger phantom, but you can see there's still lots of ring artifacts that we have struggled with and probably will struggle with for some time. But at least the images are now sharper. And just about this year, we kind of figured out the ring artifact correction. So now our images look like this. We're actually imaging a small resolution piece that we have manufactured, and we can actually distinguish 330 micron holes in our resolution piece. So we're very happy with how the images turned out. And of course, I really didn't do any of this work. So it was all my trainees that are shown in this photograph, and other people as well, but mainly these guys. They range from postdocs to graduate students to undergraduate students. So this was the evolution of our system, and I'll be showing some images that don't look as great. So please bear with me because they come maybe from 2019, 2020. But hopefully at the end, you'll be convinced that our images look pretty decent. Okay, so we basically started with looking at contrast agent imaging. As I mentioned, for KH imaging, as long as you set the thresholds in the right spaces, you actually should be able to image multiple contrast agents. Again, whether or not this is useful clinically, maybe this will be shown in the years to come, but from physics point of view, we can do it. And we are collaborating with the Department of Chemistry that basically manufactures lanthanide nanoparticles, and the lanthanides are lanthanum, gadolinium, lutetium. I think gadolinium and holmium are the lanthanides. Iodine is not. And we basically build our small 2.5 centimeter diameter phantom and put different combinations of lanthanides inside the phantom and try to distinguish them. So you basically have two different phantoms, lanthanide, gadolinium, lutetium, and you can see the cages are pretty well separated, from 39, 50 to 63 kV. And then we had iodine, gadolinium, and holmium. And what was interesting here is that gadolinium and holmium cages differ in about 5 kV. And it was maybe, pushing it a little bit because from the manufacturer, we knew that the energy resolution of the detector was about 8 kV. And now we are trying to distinguish materials that were 5 kV apart. Well, luckily we were actually successful. So this is for the first phantom, and you can see, the different contrast agents. There's basically very little cross-contamination for the high resolution and low resolution phantom, but this one was a little more interesting because this is the gadolinium image versus the holmium image. And you can see that you see both the high and low concentrations, and again, very little contamination between the materials. It was still, of course, very nice. We are quite happy, but the concentrations that we are using, you probably still don't want to inject into patients. So we have to work on the sensitivity improvement of our system, which is something that we have been doing. And a part of that was done by my other PhD student, Devon Richmeyer, who was basically looking at optimizing our system, at least with the old detector that we had. So he was looking again at the same contrast materials, but he was trying to see what kind of beams should be using, so we can filter the beam. So in this case, it's with 0.5 millimeter of copper versus 2 millimeter of aluminum, and looking at the different combinations of thresholds as well. So these are some of the images of imaging dysprosium and gold with the different filtrations of the beam, and what we were optimizing for was the contrast to noise ratio, and that might be maximized for difference beam filtering, which is a little unfortunate. So he has done some study on that. He has also looked at how wide the thresholds should be. Of course, ideally your threshold is only 1 keV. In that case, you get much higher contrast, but you basically don't get any X-rays in that particular beam because it's just too narrow. So he's figured out that the optimal bandwidth was about 9 keV for gadolinium and about 12 or I think 13 keV for gold. So it was another study that he has looked at for increasing the sensitivity of our imaging. And these are just some of the images with the optimized beam parameters. They don't really tell you very much, but we were happy that we could again distinguish the different materials and increase the contrast to noise ratio. But we are not sure about the energy calibration of the system. When we say, sort these photons from 81 to 100 keV, are those really from 81 to 100 keV? We basically got our energy calibration from the manufacturer, and it's not that we didn't trust them, but we were wondering if we can improve the sensitivity of our system by improving the energy calibration. This is work done by Pierre-Antoine Rodèche, who actually worked with the Lyon system before he joined our group. And he looked at 3 different calibration methods. So the first one was just looking at the using the basically end of the spectrum. He calls this as the calibration A, which he basically takes advantage of the KVP. So here when he says, okay, I want to image 100 kVp beam, basically the last data that you get in your system should be 100 kV, right? There should not be any higher energies. Of course, when there's pileups, we have to make sure that there is no pileup, and you have 100 kV photon, at 20 kV photon, you don't get a signal from 120 kV. So you have to make sure that the flux on the detector is very low. It's a nice method because it's relatively quick. So you just, blast, in quotes, the detector with X-rays, you analyze this, second derivative, and you get your energy calibration. The second one is using cages. So basically putting different materials in between the beam and, below, above the cage, the material will get, or the beam will get attenuated more than below the cage. And he used 3 different materials, gadolinium, gold, and lead, and basically got the cages based on that data. And the third model was called calibration C, which is a fitting model. So we had a model that was built based on some first principles by our collaborator Jesse Tange from Metropolitan University of Toronto. It's a university that just changed their name. It used to be called Ryerson University. You might know that, yeah. He basically built a model of the detector response, but it was not quite sufficient to basically exactly predict what was happening in the detector. So this is basically a semi-empirical model, and it's called the fitting model. And he was using that for the calibration and using the he was using the tungsten peaks of the X-ray source. And now he was basically comparing these 3 different calibration methods to monoenergetic data, and that can be achieved by having a monoenergetic source. So you're using barium 133 and just tape it onto the detector, wait the entire weekend to get enough counts in the detector, but we know this is going to be 81 keV signal or 31 keV signal, and then analyze the data using the 3 different calibration methods. And he also used lead X-ray fluorescence, so it was a more cumbersome setup. in which we was basically inducing fluorescent X-rays in a lead material or lead slab and measuring the X-ray fluorescence. And we made sure that this is the correct peak, and we measured the lead fluorescence with a spectrometer as well, with high resolution. And basically what the results of this study were that the fitting model provides the highest accuracy. So we are expecting the barium source at 80.9 keV, but this one gave us about 81 keV or 80.98. And also this model C resulted in the lowest root mean square error of 1.13, and the other ones were higher. The same results were found with the lead X-ray fluorescence. So it was all great. It took him about 6 months to figure all this out. But it was interesting when he applied this on CT imaging, we basically saw no difference in the calibration methods. So the take-home message here is for people that don't spend too much time on the energy calibration, it might not really matter for your CT imaging, which again, somebody had to find out the hard way. I don't know why it had to be us, but anyway, so that was kind of an interesting study, but again, very time consuming. We have to make sure that the energy calibration is done properly, but it seems like for CT imaging, it doesn't quite matter. Okay, so the next study that we have done quite recently was on metal artifact reduction, and I talked about it a little bit in the introductory slides when I talked about the work that other people have done. And we have again used our Phantom with the resolution piece here in the middle, and we replaced these water vials with metals. And we're basically trying to create metal artifacts and correct for them with our new trace replacement metal artifact reduction technique that we came up with. And this is really how the technique works. There's a number of other techniques that people have used, but I'll just talk about ours first. So we get our sinogram. Not sure if you're familiar with sinogram, but it's basically just the raw data that we get from the detector. We reconstruct an image, and again, it suffers from metal artifacts, as you can see in the middle over here. And again, we put the resolution piece in between, purposely because we want to see how we can reconstruct the resolution piece, the holes and higher density pairs with the different image reconstruction techniques. So by thresholding, you can actually identify the metal in the image, which that by itself might be actually challenging, and I'll talk about that later. You basically forward project these metals and to get the metal sinogram, metal raw data, and then you basically look at your high energy sinogram, because the high energy sinogram, again, high energy data suffer less from metal artifacts. You basically replace just the traces that were identified in this step of the low energy sinogram with the high energy data. And as a result, you get reduced artifact image. So this is, again, our TR-MAR method. Now, the referees of the journal convinced us that we had to compare it to the top-notch metal artifact reduction technique, which is the normalized metal artifact reduction technique. So we did that. And for their technique, you basically use something very similar, except you linearly interpolate the sinogram. And this is something that I, for example, done in my PhD, and other people have done that as well. You reconstruct the image as well, and then you create a prior image. So you can basically segment your linearly interpolated image into different materials. Typically, that's done 3 materials: air, soft tissue, and higher density materials. And you reconstruct your prior sinogram, you normalize it, and basically put back the traces. Then you interpolate the image of the normalized sinogram. You create your normalized sinogram, and you reconstruct that image, and eventually put the metal pieces inside the sinogram. So you can see that this normalized metal artifact reduction technique, that again is the state-of-the-art technique, is much more complex than our technique. And there's a few steps that are, basically critical to the success of the technique that we don't have in our TR-MAR. So you have to do a little bit of optimization for the modified NMR technique, but we compared our metal artifact reduction to theirs. And because we also imaged the beef short rib with some metals in there, and looked at how actually our metal artifact reduction technique does in some more realistic anatomy. Not necessarily human-like anatomy, but realistic anatomy with more contrast and more spatially interesting objects. So on the top here, we have our image without any metal. So you see it's nice and smooth, and we have this nice resolution piece, and we can see these 330 micron holes here. You might not be able to, but let's blame the PowerPoint. With metal, again, we see lots of artifacts in between the two metal screws here. But when we look at only the 100 to 110 kV image, and again, we can do that with our photon counting CT, even though there is still some artifacts, they're much reduced, right? This image is much nicer. You can see much better what's in between the two screws. Now, when we applied our trace replacement metal artifact reduction, we basically expect the area between the metals to look the same way as the 100 and 110 kV image, but the image itself should look more like, this full energy image. So it's somewhere in between. And what we can see here is that, the resolution piece looks actually very nice, and that these other cylinders here in the phantom that are filled with water actually have a pretty nice, sharp boundary. Now, if you apply the normalized metal artifact reduction techniques, you see that the image is actually smoother. So maybe if you give this to a radiologist, they would tell you that they like the NMR image a little better. We didn't do that just to make sure that it doesn't happen. But if you look at the resolution piece, for example, over here, you'll see that there's actually, the spatial resolution is not maintained, especially in the direction of the metal artifacts. And you see that there's some additional artifacts here caused by the NMR technique as well as over here. And so if you actually look at it maybe a little in more detail, so you can just plot a line and look at what your pattern between the holes and the resolution piece should look like. So this is with no metal. If we add metal, you see that the for this particular run, it really shouldn't be affected very much, but you see that there is some effect of a decreased spatial resolution. The valleys and peaks are now separated with lower values, but for our TRMR method, actually improve the spatial resolution, which also shouldn't happen, but it's nice. But for NMR, you can see that because of the interpolation that's happening in the process, you actually decrease the spatial resolution. So that was sort of one of our selling points for our TRMR method. So you can actually create the modulation transfer function. If you're doing imaging, you know what that means, and basically tells you how well we can distinguish objects at different spatial frequencies. So you can see again that for NMR, this spatial resolution was decreased compared to TRMR, which was very similar to no metal, which is what we wanted to show. Now we looked at this short rib, and again with no metal, you can see how this contrast looks like in these two different parts of the short rib. And if you put metal in there, of course, these images now get much worse because we are getting these metal artifacts. If you look at the 100 to 110 kV image, again, we can much better distinguish the metal here. But we still have some remaining artifacts because there's just too much attenuation that happens between these two screws. So we still have some remaining artifacts. And of course, these then will translate into the TRMR image. So we still have some metal artifacts, but we maintain spatial resolution. Then again, it's decreased when we apply NMR. And you can see how the images look like. And you can, somewhat see the screw. But there had to be some optimization that was performed in this particular technique. And if we didn't do this optimization, when we use no dilation on the sinogram data, this is what you would get as a result of the NMR. And so for our technique, you don't have to do really any optimization. It's just the way it is, it works. So that, again, another selling method, another selling point of our TRMR method. That was kind of fun to do that. But because we could, we also did another study with this beef short rib, and we got students who really like to cook. So why don't we scan a short rib before cooking it and after cooking it? And that's exactly what we have done here. So you can see that after you cook beef short rib, you actually basically evaporate the water that's inside of the liquid that's inside the short rib. It's kind of nice that you actually increase the spatial resolution of the bone. And so you can see the bone structure much better because there was water here or liquid, but now it's more air. So of course you can see the trabecular structure much better. You can see the whole of the temperature probe as Devon was cooking it. And you actually quite nicely see the improved fat contrast. Again, for the same reason, you're basically evaporating water. Now you're getting basically more fatty tissue rather than a combination of fatty and soft tissue. So it was actually a really interesting study because if you think about it, you get improved contrast, for fat and bone. So I just wonder what kind of implications this would have for patient imaging. I'm just kidding. We don't want to cook our patients to improve image quality, but it was fun. Okay, and not the last one, but the second to last one study that we have performed actually quite recently in August, I think, was stent imaging. So we started working with a radiologist, and he was really interested in how well we can do for stent imaging. So stents, put them in arteries and make sure that the blood can flow through the stent. And there are these tiny structures that are really complex and apparently very expensive, like thousands of dollars, which I did not appreciate. So I'm happy we have them from our radiology friend, collaborator. And he basically gave us 3 different stent types, Medtronic Protege, Cordis Precise, and Cordis Smart, that have, they're made all of the same material, nitinol, but they have different properties in terms of the strut thickness, or the wire thickness, and the lumen diameter. And they all also have tantalum markers. So every now and then along the stent, you have sets of tantalum markers just to make sure that they are really opaque in your images. And so we took all these 3 stents, we put them into straws that we filled with water just to make sure that we've got some material inside, because with air wouldn't have been as interesting. And we scanned them with 3 different scanners. GE Optima 580W, which is our CT simulator at BC Cancer. We scanned them with a diagnostic CT scanner, GE Discovery IQ, which actually have very similar properties, but we wanted to make sure that we just don't use our CT simulator, that we actually use a diagnostic scanner. And of course, we scan the phantom in our lab. So these are the images. We try to keep the parameters as similar as possible. It was important for us. We actually even implemented helical scanning on our system, which wasn't that easy either. It wasn't too difficult, but it wasn't easy. And we basically creating 2, GE Optima images, GE Discovery images, and 2 sets of PCT-CT images. One of them is the PCT-CT that matches the pixel sizes or voxel sizes of the clinical scanners. But one of them is that basically is the high resolution PCT images, because we can create images of 200 microns in voxel sizes, which we cannot do in the clinical scanners. And so, basically the limiting factor for the clinical scanners is the slice thickness that can be, at least on these 2 scanners, set only at 0.62 millimeters, cannot be set smaller than that, but we can do 200 microns on our PCT-CT. And you can see that, of course, the resolution of especially the high resolution PCT-CT stent images is much higher. So it worked out really nicely. I'll have some quantitative data as well. So we're quite happy about that. We could also create 3D volume renderings of the 3 different stents. And again, it's pretty obvious that the PCT-CT produces, much nicer structure, much more realistic structure of the stents themselves. I can also play with the window one level, but they're set all the same for all the 3 stents. And this one in particular can be seen really nicely in the high resolution PCT-CT. So the other thing we can do, because we've got these tantalum markers as they show up, like this on the energy integrating CT scanner, we can actually do KH imaging on the tantalum. I forget what the KH is, but when you do that, you're actually getting an image that's just the tantalum markers. So it might be difficult to see, it's really not difficult to see where the tantalum markers are in the EID CT. But what's really interesting that you can see that these tantalum markers appear as sort of balls, as maybe spheres. They're actually discs. And you can see them in the KH image as discs, not as spheres, as it appears to be the case for the clinical CT scanners. And you can do superposition of the KH image on the PCT-CT image. And the PCT-CT image actually does suffer from quite a few artifacts, but you can clearly visualize the markers. So we were very happy with this. We also did some quantitative analysis. So here we can look at the strut thickness, for example, for the 3 different stents. The red line shows what it should be, and the bars now show what this strut thickness was evaluated as based on the CT images. And you see that the strut thickness was always overestimated in the energy integrating detector CT images compared to PCT-CT. So that was a nice quantitative result that we actually were able to get more accurate images of the stents with photon-counting CT compared to EID CT. So we're really happy. We actually sent this to radiology, and I have to tell you that in the past, like, everybody was rejecting our work because our image quality was not up to the standard. So we were very happy that it actually got reviewed in radiology. I think impact factor is like 29 over 29. So we were very happy until last Friday when we learned that they rejected our paper. But apparently our images were fantastic. So they're all, glowing reviews, but apparently not clinically relevant, or you cannot scan patients on our system, which is fair enough. But anyway, we got it reviewed in radiology. Anyway, last thing that I will be talking about is really material decomposition. So basically what we are trying to do here is now to take this is basically comes from dual energy CT, when you can acquire images with two different energies, and then you can reconstruct the effective atomic number and electron density. Basically comes from the fact that the linear attenuation coefficient, and this is what we are reconstructing in CT imaging, is dependent on the spectrum that we are using, but also on the effective atomic number as well as the electron density. So these are just a little bit of math that we don't have to go through, and we actually modified the method by using a slightly different method. But these are the images, and that's something that I'm very proud of when my students now see this image that's from our system. They are wondering, is this simulated data or is it actually acquired data? So remember, our image quality was not very good at the beginning, and now it's actually very decent. So we're quite happy about that. So these are just images of different materials, ranging from lung of the lowest density to cortical bone of the highest density, and the atomic numbers and mass densities or electron densities are shown over here. And again, we were trying to optimize this method. Now we are basically using just two energies and trying to figure out what's the best energy combination that gives us the best agreements between the true electron densities and atomic numbers, and reconstructed electron densities and atomic numbers. So you see that these two different materials, of course, so these two different images have different contrast because we are looking at the different parts of the attenuation spectrum. So this is really hot off the Devon's computer, really. So he was looking at these two different energies, and it was 45 to 55 and 80 and 100 keV, again, just two energies. And this is what happens when you reconstruct the atomic numbers and electron densities at full image resolution. If you downsample it, then you'll end up with images that look like this. And you can see that clearly there is different contrast. So if you look at this one, which is the inner bone material, it has a different contrast in atomic number map compared to the electron density map. And you can perhaps take advantage of that in treatment planning or in diagnosis of patients. And this is just a map that shows us the agreements between the calculated values and real values. So you can see that it's actually pretty decent for the materials that we have studied. So we are hopeful here. Again, this was a lot of work that went into this. So finally, things are starting to look up, and maybe radiology can reject our paper again. But this is really exciting. Okay, so what are the challenges of photon-counting CT, the way at least that I see it? Is the energy calibration. It has to be done, but maybe it's not really that critical. What I think it's important is that we are able to select the energies that we want on a clinical scanner. And because energy calibration plays a role, I think that might be difficult to do. And from what I understand, even the Siemens CT scanner basically serves as a dual energy CT. So even though there might be 5 thresholds or 5 energy bins available, I believe the manufacturer did not enable that function. So you basically end up with dual energy CT as opposed to with photon counting detectors. So that's something that I think people have to figure out, and maybe also show that this is beneficial. We have struggled with ring artifacts. I don't want to talk about this too much, but it basically comes from the fact that the images are, well, a number of things. The detector pixel response doesn't seem to be maybe very stable, and it's non-uniform. And you think that you can correct for it one way or another, but we have tried lots of ways. Like, eventually, it worked out reasonably well. We can also see that at this point, our ring artifacts mainly happen in between the different detector modules. So it's not a single, uniform detector that we have. It's composed of a number of modules, and that's where we see most of our artifacts. But I'm sure for clinical scanners, these have been resolved. Detector stability, we don't really have much data on that, but we also know everybody has to calibrate their scanner, or at least check their scanner in the morning. Now, if you have multiple energies, that's probably going to be a little more challenging, right? How do you do QA on such a scanner? Again, I'm sure that has been resolved at least partially. but it's something that we need to figure out. And detector pileup, and I mentioned that at the beginning, that this is one of the sort of drawbacks of photon counting detectors, because they can only accept so much photons because they have to be processed at the time. So for example, and I quite did not appreciate it until recently, the Siemens scanner actually has 2 X-ray tubes and 2 sets of photon counting detectors so that they can acquire images faster. So how about photon counting CT uses for radiation therapy? As I mentioned, we can have higher spatial resolution. Here are the 330 micron pieces. You can see that you can probably distinguish them with a little bit of imagination maybe. But do we need such a high accuracy for radiation therapy, for example, for treatment planning? Probably not. Lower imaging dose, I think it depends, I guess, whom you talk to, but people don't necessarily care about imaging dose very much, so maybe that doesn't really matter very much either. Material decomposition might be useful depending on what type of radiation therapy you're performing. So for example, for low dose rate brachytherapy, even high dose rate brachytherapy, being able to identify your tissues more accurately might actually be beneficial. You might end up with more accurate dose calculations, better treatment outcomes. But in general, I'm not sure if any of these things actually matter for radiation therapy. Okay, so this is the take on ChatGPT on photon counting detector CT for radiation therapy. It actually came from Tess Reynolds from ImageX Institute just yesterday, because I was assigned to talk about the paper on PCT-CT for radiation therapy. And basically the conclusion of ChatGPT is very general. The integration of photon counting detectors with Linux may be a promising development for medical physics, but more research and testing will be needed to determine its feasibility and benefits. So you can probably say this about any new modality for just about anything, but you can see that ChatGPT was trained well for this sort of issues. So in summary, I'd say that photon counting CT offers high spatial resolution and lower image noise that transfers into a lower imaging dose. And you can use it for multiplex contrast imaging when you can image multiple contrast agents at the same time. Some hospitals are now purchasing and installing the FDA-approved Siemens Neoton Alpha scanner. Other manufacturers are developing PCT-CT. I think all the major CT imaging manufacturers are working in this area. So the killer clinical application is still not known. So it's unclear if it's worth the dollar amount. And I have tried to figure out how much these scanners cost. So apparently a regular EID-CT scanner, the high end, would be about $1.5 million. PCT-CT about $3 million. So double the cost. Take this with a grain of salt. And so the potential of PCT-CT, I do believe, needs to be now explored clinically. You know, when we have scanners that will not harm the patients, why not acquire PCT-CT data as long as we can still maintain the diagnostic quality of EID-CT? And so, yeah, I think if you guys are thinking about getting PCT-CT, you should, and maybe provide the community more information about what PCT-CT scanners can be used for. And it would be really interesting to see what can the multi-energy images be used for, because I believe it's still not clear. So some next steps for my lab, and really this is indeed the last slide. So we built this phantom that we call Casper, which is an anthropomorphic breathing phantom. I'll probably be using it to see how we can use PCT-CT for lung nodule detection. So we'll be hopefully working with people from UPenn who have 3D printed human lungs. So see if we can incorporate it into Casper. And with the ImageX Institute, I'll really hope to be looking at lung cancer imaging and basically seeing, you know, if we can do motion management for image acquisition and how small of lung nodules we can actually distinguish in a breathing phantom. And with this, I'd like to thank you, and I'm happy to take any questions if there's time.
If there are any very burning questions, right on.
I know, I'm sorry.
Yeah.
Yep.
Yeah, so thank you. It's very interesting. I was just wondering, so you said the Siemens scanner has been FDA approved and hospitals are installing it.
Yep.
Do you know for what indications?
Can you repeat the question?
Yes, so the question is if people are installing the FDA-approved photon counting CT scanner in the clinics, what indications they will be using them for, and I don't know what that will be. I suspect it'll be for indications in which high spatial resolution is needed. And that's really, I think, the main clinical benefit as far as I can tell, but I don't know exactly what that would be. Yeah, but I would say high spatial resolution again.
Question from Professor Paraxel. Paul, are you unmuted?
Yeah, thank you, Martin, and thank you, Magdalena. I was very interested with the slide you showed about the stent and the structure.
Yep.
And did I understand correctly that that paper was rejected?
That is correct. Yeah, it said
Yeah,
that we are presenting fantastic images, but rejected. Go ahead.
I don't know what the reviewer said, but what I was thinking about this is that you're basically comparing probably apples and pears, because the two GE scanners that you use, the Optima and the Discovery, are, as far as I know, relatively wide bore scanners with an 80 centimeter gantry opening. And those are scanners that are mainly designed to do interventional work and simulation. So they're not really like the high-end diagnostic scanners. So maybe that could be a reason. If you were to compare with something, I think you might be better off comparing to a Revolution with a 16 centimeter detector, or with a Siemens flash dual X-ray source scanner, something like that. Maybe that's what they thought. But if you're comparing it to what are basically workhorse scanners built for other purposes than simply diagnostic, it might be that the comparison was a little bit flawed.
Okay, well, thanks so much. And obviously, we're not one of the referees because that's not what they brought up. So yeah, I mean, the Optima certainly is an 80 centimeter scanner, and we used that because we had that in the clinic. It was really easy for us to access. The Discovery one, although we were working with our radiologist, and that's basically, he said, this is the top scanner that we have, around in Vancouver. So that's the reason why we used it. But if, I completely understand your concern, and we'll have to see if we can find a scanner that's has smaller bore, as a result provides higher spatial resolution. Yeah. Excellent. You're muted. I don't know if you're saying something.
I think we'll get to an end there. So thank you very much, Magdalena, for a fantastic talk and for coming all this way. And really appreciate it. Join me in thanking Magdalena again.
Thank you.
Thanks, everyone.
Thanks for the comments. I know you were muted, so you couldn't say what you wanted to say, but thank you.